Before we dive into the present and future of astronomy, we must look at the past. For countless years, humans looked upon the cosmos with curiosity and awe. According to the article Mapping the Sky from Ancient to Pre-Modern Times, written by the European Space Agency, astronomy is one of the first natural sciences ever studied. Glorious archaeological records such as the stone tablet of Shamash from the ancient Babylonian city of Sippar have depicted man's great interest in the outer world. For the longest time, astronomers were confined to the human eye for observations. Fast forward many generations in time, mankind started to bridge the gap between him and space. Throughout the late 1500s and early 1600s, there were multiple reports about people manipulating lenses to increase their power of sight. Peter Bond, in the Encyclopedia of Astronomy and Astrophysics, wrote that Dutch spectacle maker Hans Lippershey is most commonly known for inventing the first true refracting telescope, as he was the first who requested a patent for the device. The patent was denied due to controversy over its origin. As Peter Bond writes, the first telescope entailed a concave eyepiece that was aligned with another convex objective lens that was capable of magnifying an object by 3. When word of this spread across Europe, the widespread use of telescope was born. The field of astronomy would never be the same. A man by the name of Galileo Galilei would take this invention to the next level. According to the article Galileo and the Telescope, located on the Library of Congress website, the first telescope models were simply used for surveying and military tactics. This was just the beginning of how lenses would be arranged to view faraway objects. After hearing of the instrument, Galileo quickly created the Galileo telescope, which would magnify an object 30 times, according to the Encyclopedia of Astronomy and Astrophysics. Galileo then turned to the heavens, and the people of the world followed suit.
So Galileo was really the one who first had the creativity, but also the audacity to take a telescope and look up at the sky. And I say audacity because, of course, we know he sort of got in trouble because of that. But he really started something because in the following 100 years, there was really a outburst, an explosion of astronomy, in a sense that many after him started the same techniques, started building telescopes, improving telescopes, and that's really how telescopes got their start in astronomy. It's all due to Galileo.
Telescopes then rapidly became more advanced over the years.
There's a lot out there to discover, and this has driven the number of people that entered astronomy, that tried to work on these instruments, that tried to improve telescopes, and big improvements came very soon after Galileo. I think by the 1700s, there were already telescopes that were more than 100 feet long. People tried to improve what they could see, what the magnification was. Then came the discovery that instead of lenses, you could use mirrors, which made a big difference in terms of how compact these telescopes you could make again.
The Encyclopedia of Astronomy and Astrophysics states that in 1671, Isaac Newton showcased a new telescope to the Royal Society in London, which was the first practical reflecting telescope. Another honorable mention is the Yerkes Observatory in Wisconsin that was, and still is, the largest refracting telescope ever built with a 40-inch lens. As hopefully shown, it is very crucial to dive in and understand the early ages of telescopes before moving into the modern era of astronomy.
There is much to learn about the telescopes used in the past, but now, let's dive into the modern telescopes used by scientists today. Telescopes of the present are some of which astronomers of the past would have never thought possible. These investigative tools are more so focused on eliminating the obstruction of Earth's atmosphere than ever before, and are quite successful in doing so.
The development of telescopes is not stopping. In fact, it is still rapidly developing.
Even today's household telescopes are powerful in comparison to state-of-the-art telescopes of the past. However, the telescopes included in NASA's Great Observatory program are completely incomparable and definitely worth discussing in terms of modern-day telescopes. This group of observatories include the Spitzer Space Telescope, the Compton Gamma Ray Observatory, the Chandra X-ray Observatory, and the Visible Light Hubble Space Telescope. The release of these tools has proven to be groundbreaking, paving the way for many future discoveries, and are currently being used by astronomers all over the world. The Spitzer Space Telescope is in a unique Earth-trailing orbit around the Sun. Its focus is in recording aspects of our universe, such as distant stars and dust, that are completely invisible to the naked eye using infrared technology. Another aspect of NASA's Great Observatory is the Compton Gamma Ray. It currently orbits the Earth approximately 450 kilometers above the surface, working to form a larger, more detailed picture of the universe using wavelengths of light. According to Space Today, this observatory is credited with uncovering new sources of gamma rays, detecting over 2,500 gamma ray bursts, and allowing scientists to gain a more accurate understanding of black holes. Additionally, the Chandra X-ray, classified as a flagship class telescope, is the world's most powerful X-ray telescope. It detects emissions from stars, galaxies, as well as other regions of the universe with extremely high temperatures. The Chandra X-ray's mission was recently extended with guaranteed funding until 2025.
So all of these modern space-based telescopes are actually quite expensive, and they take years, sometimes decades to build, and preparations even for the mission before you start with the construction. So these are huge efforts, but you can see the fact that they are built, they continue to be built, tells you that there's really a curiosity and really a need for astronomers, for mankind really, to go out there and look for new things out in the sky to satisfy that intellectual curiosity. So if there is this, since there is this drive for new discoveries, it fuels all of these advances in telescopes and in space-based telescopes. And of course, generally technology is advancing. And so all of these advances, very often at least, one can take them and improve parts of astronomy.
The final telescope included in NASA's Great Observatory is the Visible Light Hubble Space Telescope.
Another thing that one should really mention is, of course, now the emergence of space telescopes. We have Hubble up there for quite a while. So advances in spacefaring are actually very important, and we'll surely see more of these space-based telescopes in the near future.
For more than 25 years, the Hubble has provided us with relevant information of space. In recent years, we've been developing technology that will overcome any precedent in the form of the James Webb Space Telescope. The future of space telescopes is currently knocking on our door. So what makes the James Webb Space Telescope different from the Hubble? The information regarding this section is supported by NASA's article comparing Webb versus Hubble. The Hubble Space Telescope orbits around the Earth at an altitude of 570 kilometers above. This is surprisingly contrasting to the James Webb Space Telescope, which will orbit the Sun 1.5 million kilometers from Earth. This is also called the second Lagrange point. This is also info regarding the differences in Kate Kushner's article. It also boasts the capability to see the first galaxies formed from the Big Bang and help provide more insight into the cosmic microwave background and around the Dark Ages. According to the University of Arizona's research, the way that JWST plans to achieve these boisterous claims is through infrared telescoping in its primary mirror system. This system will comprise 18 1.32 meter hexagonal mirror segments made of gold-plated beryllium, creating a 6.5 meter diameter mirror, 2.4 meters bigger in diameter than the Hubble. This increased size will give the James Webb Telescope a collecting area of 6.25 times larger than the Hubble. This will consequently increase the area of which the telescope can view by 15 times that of the NICMOS camera on the Hubble. Moving on to its makeup, the information present can be found in NASA's About Webb, NIRSpec, and MIRI instrument details. The various components that allow these predicted results to function are the NIRSpec or near-infrared spectrograph, which will cover a wavelength range of 0.6 to 5 microns. In order to view the various stars and galaxies, the NIRSpec is equipped with microshutter arrays that will allow the observation of 100 objects concomitantly. These microshutters operate comparably to humans squinting to focus on an object by obstructing interfering light in order to view the faintest of light from the distant galaxies. According to NASA, MIRI is another component that covers a wavelength range of 5 to 28 microns. Sensitive detectors present in the MIRI provide the capability to see red-shifted light of faraway galaxies, barely visible comets, and newly forming stars. This additional component will provide physical details unable to be detected by the aforementioned parts. Moving backward in our analysis, the part making this operation possible is the tennis court size 5-layer sunshield, led by James Cooper, the sunshield manager. His testing supports that since the telescope is infrared, it will need to be kept as cool as possible to keep obstructing light from interfering with the observations. The sunshield will keep the telescope at a temperature of around 50 Kelvin. The way the system enables this is through 5 layers of Kapton base shields specially coated with aluminum and doped silicon, allowing heat to disperse through each layer out the sides. Each layer, ergo, is colder than the last, allowing the telescope to function optimally. The info discussed above is the research and experience conducted by NASA scientists and those affiliated with. So, what are the limitations, and how will the future of space telescopes advance?
In terms of the wavelength that could be seen, or one can address that, but I think that's not the real question. I think the real question is the limits as you reach out into the universe. How far out in the universe can you see things? And here again, this is where gravitational wave astronomy, the newest form of telescope.
The limitations of telescopes are based on the range of wavelength, resolution, collecting area, and infrared. These common factors are present in viewing galaxies and stars. Thus, the further development of such allows humans to go deeper in observing the universe. These hurdles can and will be overcome slowly, first with the James Webb Telescope, but after that, how do we seemingly increase the development of something that's reached a peak?